And just as a heads up, everyone, first of all, Carlo, do you feel comfortable with people asking questions during the talk, or would you rather wait until the end?
No, please do ask questions. If it goes long, I stop and then we continue after.
Perfect. Let me also mention, everyone, that we do have a form for anonymous questions in case you don't feel like doing it explicitly. So if you feel more comfortable, that's also a possibility, and the link for that will be posted in the chat, and has already been posted in the chat, but it will be posted in the chat again more often. So yeah, are we recording? Yeah, okay, good. Then let me start. Then I have to fulfill the protocol obligation of introducing Carlo, which of course is a very difficult thing to do. In some sense, he needs no introduction, but I will still do my job and try to keep this at the minimum. So Carlo's alma mater, in some sense, at least where he did his PhD, was University of Padova in 1986. He's currently professor in the Western University in Ontario, possibly still in Marseille as well, and also holds a visiting chair in the Perimeter Institute. Of course, Carlo is an accomplished researcher in theoretical physics, and I will, of course, come back to this point soon. But I would also like to touch on things that go beyond this. Some of Carlo's interests also touch on, of course, history of physics and philosophy of physics, epistemology. I remember Carlo had a more or less recent paper on Aristotelian physics. And Carlo is, of course, an important contributor to scientific outreach. He has a number of popular science group books, which is, of course, an important effort from the physics community to reach people that might have interest in physics, but they are not physicists themselves. The most recent book, his Helgoland, on the topic of quantum mechanics and its many interpretations. Finally, before the physics part, I cannot resist but to touch on a fact that I learned about today, is that Carlo recently actually co-released a song in November last year with an Italian band, Prima Donna. So that's maybe something that you might want to check out. But of course, we are not here today, despite Carlo's surely amazing qualities as a musician. We are not here today because of Carlo's qualities as a musician. We're here because Carlo is one of the founders of Loop Quantum Gravity, together with Ashtaker and Smolin. And I believe this is precisely what we will hear about today. So Carlo, please go ahead, and thank you very much.
Thank you, Jose. This was very nice. Thank you, very kind. I'm a horrible musician, and I was involved in the music because the others, the real musicians, are good musicians. So yes, I'm going to talk about loop quantum gravity, and so let me start by thanking all of you for this invitation. I know that mostly you talk about yourself, young people, and I'm the old guy, so I'll do my job as an old guy, giving you the way I think about loop quantum gravity. So this is not, of course, a class in loop quantum gravity. I'm not going to, define thing and derive thing. I'm giving an overview, the structure of the theory, why I think it's interesting, and then also at the end a little bit of sort of framing it in the context of other possible approaches to quantum gravity. Good. And if you have questions, do stop me, but at the end I will be, I have time. So if you want to ask questions, discuss also not just technical questions, but also perspective things, general ideas, comparison, I'm happy to to spend some time with you guys and tell you what I think. Let me start by saying what is loop quantum gravity, because not all things that go under the name quantum gravity in the literature are actually the same research program with the same research aim. So this is what I think loop quantum gravity is, what it is in my mind. Let me just read it. It is a consistent theory of gravity and matter fields, quantum theory of gravity and matter fields, whose h bar going to 0. So classical limit is general relativity, and by general relativity I mean the real physical one in 4 dimensions, Lorentzian, with its standard matter coupling, and whose non-gravitational limit is conventional quantum mechanics. Now this seems sort of neutral as a characterization, but I want to it's not at all. So a number of points are important here. The first is that this is a consistent theory, meaning that the claim of loop quantum gravity to be interesting is not that there's a unique fixed procedure given a classical theory to construct a quantum theory, so that's for sure the only possible quantum theory of gravity. But it's the other way around. I mean, it's a century we search for, a half a century we search for a theory of quantum gravity. It's very hard. It's not easy. I think we don't have many. We have very little possible theory of quantum gravity. This is one possibility. So the question, why is it defined this way and not in another way? It's not a good question with respect to the aim of the theoretical research. It is a good question with respect to the empirical verification. I mean, if we happen to have more than one consistent theory, then we can ask nature with experiments which one works best. I mean, we can find try to distinguish them empirically, and this it's going on. It's going on, as I will say at the end of the talk. Second point. Consistent means both coherent within. This is a well-defined mathematical formalism, but also that there is a conceptual way of thinking about that. How do we think about the quantum theory of gravity, what it is to measure space-time, and of course consistent in the very simple sense that perturbative quantum general relativity done usually by perturbing around Minkowski space is inconsistent because there are ultraviolet divergences, as you all know. So the main point, the 0 point, the essential point about consistency is that there should be no ultraviolet divergences, and in quantum gravity there are no ultraviolet divergences, and is also consistent in the other sense. But the key is one. Next point, it's a theory of gravity and matter fields. But careful, this does not mean that it's a unified theory. The standard model is a theory of the weak and strong interaction. It does not unify the weak and strong interaction, right? They're two different things, two different fields. There's a Weinberg-Salam field and the gluon field. Here's the same. It's not a unification. A unification is something else. Unification is the idea that there is a simple structure from which all things we know in nature derive. I don't know, string and everything is made by strings. This is not at all the aim of loop quantum gravity. My own opinion is that we are very far away from having a unified theory of the world. Nothing has worked so far in terms of unification. So maybe there is, but this is something for next generations, not for us. It's a very specific problem, which has nothing to do with unification, which is what happens when the gravitational field has behavior that we cannot disregard its quantum behavior. What happens saying to a black hole? What happened at the end of the Oki evaporation? What happened at the Big Bang? The physical questions that involve quantum property of gravity, and that's what loop quantum gravity is meant to describe. Like QCD is meant to define the quantum properties of the gluon fields and the strong interactions, not to unify with electromagnetism. Next is I just want to stress that standard matter couplings only because you know, there are polemics around, and you often read that loop quantum gravity is only about gravity, pure gravity. The loop people don't know how to do matter field. That's completely false. I mean, the people who say that is people who looked at loop quantum gravity 30 years ago and have never looked since. So it is the theory can be formulated with matter fields. I will not go into the coupling with matter fields much unless you ask, but it is in the books. And then there's a subtle point which I want to stress upfront because it's a source of confusion. Is loop quantum gravity a quantum theory, a conventional quantum theory? Well, depends what you mean by a conventional quantum theory. Certainly a quantum theory, but it's not conventional if by conventional quantum theory you think a theory defined with a Schrödinger equation with external time that evolves. And there is a lot of people who, especially in the philosophy world, but also a little bit in some corners of the physical world, who says, we cannot do quantum gravity because what we do is not the standard quantum mechanic with evolution in an external time. Of course it's not, because general relativity is not that way. So if you want, it's strictly speaking, it's a generalization of quantum mechanics, which allows us to describe temporality in the way general relativity is describe temporality, and which in the appropriate limit is a standard quantum mechanics. So this is what loop quantum gravity is. It's a consistent theory which has the two limits as we want. Now, how is the theory? What is the theory? The theory is the way I view it. I mostly work in what is called the covariant version of the theory, not the canonical version of the theory. So it comes in two flavors. Now it's more than a decade that they work in the covariant version, so I'm going to talk about that. The structure of the theory is pretty much the structure of a standard quantum mechanical structure. Think at your preferred quantum mechanical model, where is QED or the harmonic oscillator or the hydrogen atom. There's a state space, which is a Hilbert space, in which there are vectors which we write psi or represent state in some sense. It's a bunch of operators that represent, describe the kind of thing we can measure. So when we interact with a system, here we interact with space-time, with gravity, we can measure things. We can measure the gravitational field. We do it every time. LIGO measures the gravitational field, but also when you measure distance, you measure the gravitational field because it's the integral of the square root of G mu nu. And so the state space and operators are the kinematics of the theory, like, for the Schrödinger theory of a hydrogen atom is the wave function and the operator x and p d over dx. And the dynamics is given by giving transition amplitudes. So it's not given with a Hamiltonian in the covariant formulation, is given by giving transition amplitude, not a Feynman if you want. You have the amplitude going from from one value to another value. But careful, these are not strictly speaking amplitudes in time. And the way to think about them in loop quantum gravity is this blue is a space-time region. So let's say that this is space in the horizontal direction and time in the temporal direction. And what we want to describe with loop quantum gravity is a process, this red area, a process which is limited in time and limited in space. So think, for instance, a black hole that forms, goes through some quantum stuff, and whatever happened next, okay? So the amplitude describes this process, and the states are the boundary of this process. So at the beginning and the end. And in general relativity, this boundary don't need to be constant time surfaces. In fact, there's no meaning, no sort of objective meaning in constant time surfaces in general relativity. So the clean way to think about that is to take surfaces which close a finite space-time region, and it's convenient to take this surface space-like. And the quantum state is just whatever is at the beginning of the end of the process, which means if you think think quantum mechanically, this is the quantum system. And outside the quantum system, you make measurement before and after, and you compute the probabilities associated to possible set of outcomes, the relative probability. And the state can be either thought as initial state or a final state, or as it is convenient, just mix the two, sort of take the tensor product of the initial and final Hilbert spaces and view the state as the state all around it. Now, the key point is that in gravity, time is one of the variables that to measure at the beginning or the end. So if you one clock, you will have some value at the beginning, one value at the end. If you have three clocks, they will have their histories, and they will not give the same value, because in general relativity clocks do different things depending on what happened to them. So this process is not labeled by an external time variable. The time variable is one of the the time variables, plural, are among the observables that you can measure on the status among these operators here. Good. So the next thing to have clear to understand loop quantum gravity is that the theory is defined via a sequence of truncations, plural. Why? Well, this is very much like in quantum field theory. In fact, in quantum field theory, we always do that. If you think of lattice gauge theory, we have two good ways of defining quantum field theory. One is on the lattice, and one is a Feynman expansion with the Feynman graphs. And in both cases, what we describe, what we have is a sequence of truncations. With a lattice, we define the theory on the lattice, and then we, in some sense, we say that the more the lattice is rich, the more you capture nature. And Feynman graph is the same. You have you compute the transition amplitudes, summing Feynman graphs, and the more you sum, the more you have well-defined transition amplitudes. But we always work with truncations, and so we do in quantum gravity. So we have a family of Hilbert spaces that increase the truncations, labeled by some gamma, and one can do some fancy math, but in some sense, the full Hilbert space is the limit of that, which is, can be done with some fancy math. The observables are defined on this truncated Hilbert space. I'll tell you in a moment what is gamma. And transition amplitudes are defined also with truncations. On the same boundary Hilbert space, you can have more refined, more and more better approximations with refining the truncation. Now, what are these truncations? Well, the beauty, and let me just say, I want to emphasize the point I like it here. The beauty is that you can think either that what is going on here is like lattice gauge theory, or that is like Feynman graphs. And because we are doing the quantum gravity, the quantum theory of space-time itself, the two things match, the two become the same. Let me show you. The truncation of the states is labeled by this gamma, where this gamma is a graph. A set of the combinatorial structure given by a set of nodes, of points and links, nodes and links. Okay, and one way of thinking about that is that each point is a point in space, and the links say who is next to one another. So this is really a truncational space, like in lattice gauge theory. It's exactly what we do when we discretize a quantum theory on a lattice. Of course, it's a discretization because instead of infinite number of degrees of freedom, we have a finite number of degrees of freedom there. Okay. I will come later to a point in which there is a key difference in between lattice gauge theory, but so far is exactly the same thing. And then the transition amplitudes are also described with a discretization. It's called C now, where C is, you can think as a four-dimensional discretization. The points and the links, which are called edges in this time, and then there are also surfaces. And one way of thinking about that is that this point here is a vertex. It represents a piece of space-time, and two space-times are connected next to one another when there's an edge between the two, and a set of space-times can enclose a two-dimensional region, which is dual to the surface here. What I'm saying is that this can be viewed as a discretization of space-time, but can also be viewed as a history of the states defined on a spin network. So if you on this graph here, so this line in time is the history of a node, the surfaces are the history in time of a link, and then this discretization is really like a Feynman graph. So since we're doing quantum mechanics of space-time, the discretization of space-time is a history of the discretization of the boundary. Now, the actual theory is given by defining mathematically this Hilbert space, this operator, and giving expression for this transition amplitude here. So let me give you a little bit of details of all that. The Hilbert space associated to one of these graphs here is something that, if some of you are familiar with lattice gauge theory, is exactly like the Hilbert space of a lattice gauge theory, of an SU2 lattice gauge theory, done canonically, a la Wilson-Kogut, if you've studied lattice gauge theory. So this means that the states, psi, are wave functions of variables which are associated to the link. There is an SU2 group element for each link. SU2 group element are called little h. So H sub L, you have a SU2 group element associated with each link, and the quantum state is just a complex function of all that, with a symmetry which is related to the gauge symmetry at the nodes. I don't want to go into the detail. And then there are some operators which are the natural operator that you define on this kind of things, which are in lattice gauge theory would be the electric field in the direction of the links. In gravity are just the geometry, because the operators are the thing that in the classical limit is the metric. So pieces of geometry. And I'm not going into detail, but this is a beautiful piece of mathematics, because these operators can be obtained as a quantization of the gravitational field, G mu nu, or more precisely the tetrad, the square root of G mu nu, or more precisely the triad, which is the gauge fixed version of the metric. And this operator here satisfies property that make them exactly Penrose metric operators, which are the way Penrose back 30 years ago constructed a quantum theory of geometry on graphs in terms of operator of this sort here. And the set of operators is operated a little by links, by link. So on a node, on a link, there's one operator per each link, and a set of operator around the node have a property, but from their definition, that characterize them as a quantity that define the geometry of a polyhedron. So what you can think about this graph here is that these operators here give it a geometry, and the geometry is like giving a lot of polyhedra, say a tetrahedron or more complicated geometries outside. So this operator give a geometrical. Of course, each one is flat, but the way you put it together, you can get curvature. From those basic operators, you can construct the geometrical quantities, the volume of these things here, and the areas of the surfaces defining this. Now, so far, all I've said about discretization, about polyhedra, is just a discretization of a continuous geometrical space. But now comes the point. These are operators, they have the space, so they don't commute, and they have a spectral theory. So there is spectra associated to each operator, and this spectra can be computed. And the result of the computation of the eigenvalues is a key result number one of loop quantum gravity, which is that the area has a discrete spectrum. This is a spectrum, and the volume has discrete spectrum. It's a little bit more complicated to calculate, can be calculated, just a little mathematics, which means that in each discretization, whatever you discretize, you always have a minimal length, a minimal area, a minimal volume, which means that this, as a quantum description of geometry, predicts a minimum size of anything, okay? Minimum area, minimum volume. And this is a root of the ultraviolet finiteness that we will see in the dynamical part. Let me just close this kinematical part. There is a set of states. The Hilbert space admits a basis, which is obtained by diagonalizing area and volume. It's called a spin network basis. It's written this way here, it doesn't matter. Where area and volume are discrete. But one key point is that, take a tetrahedron here. Tetrahedron has one volume and 4 areas, and these are a complete set of operators, can be diagonalized, but there are 5 numbers. Tetrahedron classically has 6 variables that characterize its geometry, because each length you can make it longer or shorter. So one is missing. What does it mean? That you cannot sharply, in the quantum theory, have a value associated to all 6 quantities. So it's like angular momentum theory. So therefore, the geometry is fuzzy in the small. So you see, it's a standard quantum theory. Eigenvalues are discrete, operators do not commute, geometry are fuzzy, and the generic state is a quantum superposition of these things. This is a quantum theory of 3-dimensional geometry. And last key point, these quantum states are not to be thought the quantum state in space. They are the quantum state of space itself with its geometry. Now let me go to the transition amplitudes. the transition amplitudes have a long story because there have been a number of attempts to define them through the years, with the sense that there was something wrong all through the years until this definition was found here of the transition amplitudes, which was obtained in different manners. One way of obtaining it is just sort of through a discretization of a Einstein-Hilbert action. One way of obtaining it through a canonical quantization and implementing the constraint in some way. It's a long story. But finally, given some states on a boundary, so on the initial, say, and final states, and remember, the states are functions of SU2 variables, so the transition amplitude can be expressed as functions of the SU2 variables of the boundary, which you can glue with states. This is a definition of the transition amplitude, which has all the properties that one wants. It's very similar to gauge theory. You're integrating on internal variables, which are both SU2 and SL2C variables. There's a vertex amplitudes, which is the only sort of non-trivial part of the story. So to every vertex, every piece of four-dimensional space-time, there is an amplitude, which depends on the variables around it, which is a relatively simple expression, which I'm not going to define explicitly because it's written in terms of representation, infinite dimensional representation of SL2C. You see, this is a trace in a certain representation of SL2C, and the core of the mathematics of the theory is a map between SL2C representation and SU2 representation. It's given in a canonical basis. So there is a mathematics to learn to know how to use this thing here. But everything is well defined, and the key result of all that. Oh, sorry. No, that's not what I wanted, is that it is, everything is finite. Now, I just want to, I added this slide here. I don't want to go to bore you with math. This is actually very simple, but to tell you why this works. And why this works, I mean, why this definition here of the transition amplitudes actually gives something finite as it is, without any further limit. The only limit is that you can refine the four-dimensional triangulation. You can change the C. There is a reason in that, which is the following. Just one technicality, very simple, but in my opinion, it is the core of the story. Take an harmonic oscillator. This is the action of an harmonic oscillator. Discretize it, and you introduce a lattice spacing A, and write the path integral. Now it's convenient to change variables from A to omega, which is just a scaled, it's a big omega, which is just the frequency scaled by A. And then you show that to get the actual transition amplitudes from the discretized path integral, you have to take two limits. You have to increase the number of steps, that's your discretization, is n, and go on a critical point, as everybody knows. Okay, in quantum field theory, you have to go on a critical point. You have to take a limit of something. And when you do discretization, to recover and the continuous theory, you have to go to a critical point. But now, take the same harmonic oscillator, but write it in a discretized form. So instead of having a variable q, now you have two variables, q and t. You promote t to a independent variable, and you evolve in a tau, which is unphysical. You do the same game, and something absolutely magical happens, which is the discretization, the lattice spacing disappears from the action. So the same transition amplitudes can be computed without going on a critical point, just by taking n to infinity. And this is general. If you do the discretization correctly, you can recover the physical transition amplitude, this is a harmonic oscillator, we know what these things are, without the need of going to a critical point, just by increasing the number of steps, okay? And that's why general relativity, which is a parametrized theory, doesn't need to be on a critical point. And that's why the transition amplitude that I gave you before work and are defined as they are. So this was the definition of the theory. That was the most technical thing I've done. How I'm doing with time? Oh, pretty well.
Very well.
So I want to close with various comments about what one does with that, how one got there, and comparing with the overall picture of the research in quantum gravity. This is a slide with a very rapid overview of the history. Quantum gravity started, it's very small, I don't know if you see these things, started back in the 50s with Meissner, who's the first one who wrote this, sorry. Coming in the way. Who wrote the functional interquantum gravity. So essentially, what I've given you with transition amplitude is a version of the functional interquantum gravity, discretized sort of a la Regge, but in a way that works better than Regge. As you all know, in the 60s there was the basic development of the idea of quantum gravity with Will DeWitt, and in the 70s. Penrose came out with this spin geometry theorem, which is the core of the spin network geometry. This way of describing geometry, three-dimensional quantum geometry that I told you. So this is sort of the prehistory. Loop quantum gravity started in the 80s with a classical work by Ashtekar with a complex variable, and then with Smalling, it exploded because it realized that the Will-DeWitt equation has solutions once rewritten in the Ashtekar variables, and this solution are loopy. Okay, so the idea is say, okay, good, go to the basis of this solution, see what happened. And this was the beginning of loop quantum gravity, and the key result of the discretization of the geometry in the middle of the 90s were the calculation of the spectral problem, and in the 90s also the idea of doing the covariant version began. The actual expression of the transition amplitudes is 2008, after a sequence of attempts, and shortly after there was the proof that the limit of these transition amplitudes is in fact general relativity. It's one get the limit in the end, and theorems about finiteness came up shortly later. Now, the key results of the theory are these: the amplitudes are finite, the boundary state represents a classical geometry, the boundary geometry of discrete spectra, and the classical limit of vertex amplitudes is exactly the Regge Hamilton function, which is in turns as a limit of general relativity. So the way to think about this is that this truncated amplitudes approximate exact amplitudes, which we don't know how to write, and there is a classical limit which gives a discrete classical theory, and which in turns, in the refined triangulation, we know gives general relativity. These two limits actually, it has been understood recently, have to be taken together. They cannot be nicely separated in this picture. But this gives the idea of how things work. Theory is Lorentz covariant. It can be coupled with fermions and Yang-Mills. The transitional amplitudes are hard to compute, even if they can be written in 10 different ways. So now there is a beautiful numerical program which has been developed, the codes for computing that, and a lot of numerical activity in that direction. Okay, so that's the theory. What does one do with this theory? What is the physics? The domain applications are two. One is cosmology. There's a huge field which is called loop quantum cosmology, which essentially consists in taking the theory, some of the result of the theory, and approximate dramatically to a cosmological situation and see what happens. And the pretty solid result is that the Friedman equation gets corrected with a term, and this term has a result that if you evolve the state back in time, it bounces instead of the Big Bang. So the theory seems pretty robustly to predict a bounce instead of a big bounce instead of a Big Bang. If there was contracting phase and then an expansion, and a lot of work. It's sort of expanding around this and using again result from the field theory to try to see if in the CMB one can predict something different from the standard cosmological theory, especially in this area here, of course, and compare with observations. It's a big industry there. A lot of work has been done in black hole thermodynamics, deriving the Beckett-Hawking entropy. And the work in which I am focused right now is also on black hole. And this is what I find most interesting going on right now. It's about what happened to all the matter that falls into the black hole and what happens in the future of the black hole. So there is a standard picture that says if you have a star that collapses, you have an horizon that form, there is Hawking radiation, the star evaporates, and then it disappears. This picture, I think, is silly because we have no theory whatsoever that tell us that the thing disappear. I think that the credible picture is something else. There is a quantum transition amplitudes to something else. And if you work through the theory, you're exactly in the situation in which you can use the covariant logic. Remember this picture here. This is the logic of the theory. You have an external region where you can forget quantum gravity because the classical approximation is good enough, and then you have a region where is a quantum gravitational process. That's how we use quantum mechanics all the time, right? So that's exactly the way to think about black holes, because where it is here, because we have a star collapsing, an horizon forming, and then of course there is the quantum region, which is the high curvature region. So you just enclose this into a compact domain, right? Space-time domain. Outside, it's the classical approximation is good, and you have to compute what happened. And this can be done with the transition amplitudes, which I gave you. And there's a lot of work, analytical, numerically, to compute the transition amplitudes to see what the theory is telling us about the probability transition and so on and so forth. And perhaps one of the things that is my secret hope, is that this might be connected to dark matter, because what the theory seems pretty generically to predict is that the interior, through this transition, becomes the trappezoid region becomes an anti-trappezoid region. So a black hole becomes a white hole. So if you're outside, you see a black hole becoming a white hole. But of course, this happened at the end of the evaporation. So the black hole has become very small. So you have a very small white hole that there are reasons to believe, theoretical reason to believe, that it's going to live for a very long time, a time much longer than the Hawking life of the black hole, emit very slowly. And so what the theory predicts is that old black holes are all become remnants, those small little things, Planck size, microgram, that live for a very long time, which is exactly how dark matter shows itself. So could this be a candidate of dark matter? With many candidates of dark matter, that's another possibility, is one challenging hypothesis that come from the theory. Good. So this is all about loop quantum gravity. I've talked for 35, 40 minutes. So I take the last few minutes before taking your questions by saying something more general. So I told you about loop quantum gravity, structure of the theory, characteristic and applications. Now, you guys are doing this looking at quantum gravity in general. So loop quantum gravity is just one chapter in the research of quantum gravity. And as you all know, there are all sorts of approaches to quantum gravity. This is a scattered list of many of them. It seems daring and seems there are too many, but I think there are less than one thing. First of all, there are connections about that, and one can organize the approaches to quantum gravity, depending of what are the physical hypotheses which are put into the theory, like violation of Lorentz invariance, like violations of quantum mechanics, existence of supersymmetry, high dimension, extra stuff. And perhaps two main areas which I call no infinity in the small and infinity in the small, which are the two major hypotheses about quantum space-time. This green one is think about asymptotic safety, is a hypothesis that there are degrees of freedom all the way to arbitrary small scale or high energy, okay, to infinity. While if you want, both loop quantum gravity and string theory are characterized by the physical result, not hypothesis, because this both comes from a result, a quantization of string or a quantization of the geometry, that in some sense, there is no physics beyond the Planck scale. There are no excitations beyond the Planck scale. In loop quantum gravity, this is very physical, very direct. It's for the same reason in which a harmonic oscillator doesn't have oscillations less than 1/2 h bar omega. For the same reason, space-time doesn't have volumes less than something. And in string theory, something similar happens, right? Because in a sense, if you want to squeeze a theory, if you want to squeeze a string too much, then the higher the other modes of the string get excited. So again, you cannot probe regions smaller than h bar, than the Planck length or the string length. But so there's some connections and some clear distinction between all the current approaches. But what I say is that many of them are not really quantum gravity, are just ideas. I mean, do classical theory because maybe one day will be useful for quantum gravity. Some of them are very radical, like Penrose thinking that quantum mechanics is wrong. And more important, we do have empirical inputs. And empirical inputs have come in the last years, or decade even, numerous, and have completely disrupted the situation that was 20 or 30 years ago, that we have no empirical input for quantum gravity. Let me mention this. The first one, and the most important one, is that supersymmetry is not where many expected. And this is a major drawback for string supersymmetry and all related research in quantum gravity. This is not in the sense of Popper, a falsification of string theory at all, because of course, we know from philosophy of science, you can always take a theory and, adjust it to the result. But rarely we have a falsification. The way research works is that some ideas become productive and tell us something. And when an entire community is convinced that something should happen and it doesn't happen, I think is a strong indication, and people have been talking about the crisis of physics, that the underlying ideas were wrong or not right, not completely right. But of course, I remember articles even in France in Le Monde, the crisis of physics. This is not a crisis of physics. This is a crisis of that particular research director that expected supersymmetry. People in loop quantum gravity did not expect supersymmetry since decades, and thought that no, there is no reason for, there's no strong reason. I mean, supersymmetry is a super interesting hypothesis, but it's not so compelling after all. Naturalness works sometimes, but not always, and so on and so forth. So this is a difficulty for some approaches. Another difficulty, which I think is not emphasized enough, is that same community expected the cosmological constants to be negative. So much that when the cosmologists found it, measured it positive, many theoreticians didn't believe the cosmology. Took a Nobel Prize before convincing that they were right. And so much that today, a huge amount of papers are published under the hypothesis that the cosmological constant is negative. Every time you read ADS in a paper, is assumption that the world is not what it is. With the idea, oh well, but maybe tomorrow we'll find it better. But the cosmological constant is positive, loop quantum gravity can be written with a positive cosmology constant, no problem about that. In fact, it cuts away the infrared divergences. It plays a big role in the theory. And again, I think that we should listen to nature, not to physical review. Other big empirical inputs that come in is that this come from astrophysics. There have been a full campaign of research in astrophysics to measure violations of Lorentz invariance, because there were papers and papers and papers about Lorentz violating quantum gravity. It's you can get finiteness by Lorentz violating, right? Rojava theory and connection. Well, where the Lorentz violation was expected, it hasn't come out pretty strongly. Now there are big limits. So once again, these are all empirical results that put difficulties on research directions. And I think if we are scientists, we should listen to nature, not to our fancies. And recently, another huge empirical input from nature has been the merging of the neutron stars that has been detected simultaneously by LIGO and by electromagnetic detectors in very many ranges of the electromagnetic spectrum. The two signals arrived virtually at the same time, which means that gravitational waves and electromagnetic waves go at the same speed, which cuts away, this is real falsification, of a huge amount of literature that was exploring alternative general relativity where this does not happen. So a lot of FFR, variation of GR theories, which were studied by people spending their life studying them, they're not right. Okay, still some alternative general relativity is compatible with that, but when you develop a research program that strongly indicates something and it doesn't happen, I think it's that good science says just look somewhere else. Now, I'm not saying, of course, that there are positive indications for loop quantum gravity out there. There isn't any. Okay, there isn't any positive indication for any approach to quantum gravity, but none of this affects loop quantum gravity in any way. So in a sense, I think loop quantum gravity is a much better situation empirically, not because it will got direct support, because the strongest competitors are much in trouble in the last years. And I also want to mention something which has not been measured, but there's a hope to measure in the future, few years, nobody knows, which is the quantum superposition of geometries to be measured in the laboratory, in a non-relativistic case. This is a spectacular development in the last years. It's a sort of a regime that nobody paid attention much. There is a non-relativistic regime, quantum field theoretical, in which you can put into superposition quantum fields and measure system getting entangled through that. Which would rule out, if it is measured, and many people would bet that that's the result would come out from the experiment, would rule out all the speculations about gravity being classical, because this is an effect which is not predicted by all the theory I know in which gravity is classical. Good. So we have many directions for quantum gravity, but many are in tension with recent inputs. Many are extremely incomplete, not theories, are just half-cooked idea. Maybe from this will go somewhere. Many, and I also want to mention this separately, have been very disappointing on their own expectation. Remember that, when I was your age, guys, string theorists were sure that they would be able to compute all the standard model free parameters in a few years. 40 years have passed and nothing has happened whatsoever. So the number of theories, but there are well-defined quantum theory of gravities, unproven, to be developed, not yet clear, but definitely complete quantum theory of gravity, which might be right, like loop quantum gravity. I close with what I like about all this as a theoretician. If you look at the theory at the stage it is now, I think it's beautiful. It has all the magic of loop quantum gravity that fascinated me when I went into the field. The theory is formulated, if you think of the equations that I gave you, there's no time variable. So it's a fully time-lapse dynamics in the sense it's a relational dynamics. Describe very well the world in which we are without an external time parameter. Space is not a variable. There are no coordinates in the theories. What we call space emerged by the quanta of gravity attached to one another. So in a sense, space, time, matter, everything, geometry, it's all quantum fields. It's not a unified theory in the sense that there is a single thing that becomes fermions, Young-Mills, and gravitational fields and so on, but is a conceptually unified things in which there is a single set of entities, which are quantum fields, general covariant quantum field theory, which gave rise to fermions, Young-Mills, gravity, space, and time. The no infinity is in both sense. It's ultraviolet finiteness, but also you don't need to go to asymptotic infinity. You can do everything in local processes. And there are no things in the sense that what the theory is about, if you think about, but because you describe evolution, you decide processes, there's no a priori way of identifying the same thing across the process. So the theory is about processes, not about things, strongly. And there are no external observers in the sense that if you think about quantum gravity this way, you are not allowed to think about the observer outside the universe. There's no wave function of the universe here at all. There is pieces of space-time seen from the outside. And so there is how one part of the universe observe another part of the universe. All this, I find the beauty conceptual structure of quantum gravity in the way it's used in loop quantum gravity. So my last slide is just my two books on this. If you want to go into that, I have a old 2004 book. It's called Quantum Gravity. It's about loop quantum gravity, which is more detailed, conceptual, all the stories, and a more recent work where there is the transition amplitudes that I told you, much more introductive, much more straightforward, much more simple. From the conceptual points, how to do a theory without time and so on. There's a very recent November 22 sort of conceptual foundation loop quantum gravity paper, which I've written with Francesca Vidotto. And there are schools, loop quantum gravity, every couple of years. There is regular loop conferences. And Francesca Vidotto has a website with all the sort of 40 or more groups in the world that work in loop quantum gravity, in case you're interested. So this is an overview, how much time I've used, so much, from 50 minutes. So let me stop here, and I'm happy to take all questions.
Thank you very much, Carlo.